Okay, so let's start. Am I audible? Can you hear me? Okay, so what we'll do today is first we'll solve some question based on week six contents and its assignment, and then we'll solve questions based on week seven's contents. So let's start with the first question from week six. So the question is, select the incorrect option or options for the Merkel-Damgard construction. The options are: it employs a single stage approach for the transformation. Option B is: the construction always adds a padding to the end of the message that depends on the message length. Option C is: the initial vector IV used in the construction has to be fixed. And option D is: collision resistance of the transformation is independent of the collision resistance of the compression function used in the construction. So since these questions
सर
are from, yeah,
लो
can you repeat that? Can you repeat that?
सर आपकी आवाज ढंग से नहीं आ रही है। आवाज
Okay, okay,
तेज नहीं आ रही थोड़ी।
okay. So let me try to reach you. Is it better now?
यस सर इज गुड।
Oh, okay, great. Okay. That's what, I'll just go over the first question again. The question is, select the incorrect options for the Merkel-Damgard construction. The options are: it employs a single stage approach for the transformation. The construction always adds a padding to the end of the message that depends on the message length. The initial vector or IV used in the construction has to be fixed. And option D is: collision resistance of the transformation is independent of the collision resistance of the compression function used in the construction. So since the first few questions are from week six assignment, you might have already attempted these questions in the assignment, and you might already know the answer. So would you like to answer these questions? And if yes, you can put the answers in the chat.
सर सर मेरा एक डाउट था कि
Okay.
जैसे इस कंस्ट्रक्शन में ना जैसे जो हम कॉलिजन रेजिस्टेंट हैश फंक्शन का यूज करते हैं ना
Hmm.
यूज तो सर वो तो हमारे पास वैसे नहीं है ना, मतलब ये प्रैक्टिकल कुछ कंस्ट्रक्शन है क्या मेर्कल?
Okay. So the Merkel-Damagat construction is practical provided you have a hash function, right? Sorry, provided you have a compression function. Okay.
डू
Now,
वी हैव कंप्रेhension
exactly.
फंक्शन?
Like PRGs, PRFs, almost anything that we have seen in the course, we don't have a compression function which we can prove is collision resistance. However, there are some practical constructions, and for those constructions, we haven't been able to find any attack till now. So, for example, SHA, MD5, etc., are examples of compression functions for which we do not know of like any attacks till now. So just like stream ciphers, block ciphers, and PRS and anything else, we don't know of a construction that we can prove is theoretically secure, but we have practically secure constructions. So does that answer the question?
ओके सर।
Yeah. So basically, what you can do is you can replace that compression function with any practically secure, any hash function which is practically corrosion resistant, and that would give you an overall construction which is practically corrosion resistant. Yeah. Okay. Yeah, so coming back to this question, so let's go over the options one by one. The first option is it employs a single stage approach for a transformation. Well, this is incorrect because it it uses two stages. In the first stage, it cons- the first stage is the construction of a collision resistant compression function, and the second stage is to use this compression function and domain extension to construct a collision resistant hash function. So option A is incorrect. About option B, the construction always adds a padding to the end of the message that depends on the message length. Well, this is true because if you recall, that construction takes a message X and divides it into blocks of length n. So let's say the length of the message is not divisible by n, then it would add some padding to the uh, end of the message. So it always adds some padding to the end of the message depending on the message length. Even if the message length is divisible by block length, it would add an extra block. So padding is always added. That's true. Option C is the initial vector used in the construction has to be fixed. Well, yes, we saw in the class that the initial vector in this construction is fixed. And option D is collision resistance of the transformation is independent of the collision resistance of the compression function used in the construction. This is false because if the function underlying compression function that we use in the construction is not collision resistant, then the overall transformation need not be collision resistant. In fact, this is an if and only if statement. The overall construction is collision resistant if and only if the underlying function is also collision resistant. So D is also incorrect. So we should take options A and D for this question. Is this fine?
Yes, sir.
Okay, yeah. So let's move on to the next problem. So choose the incorrect options. Hash functions can either be used for compression or expansion, but not both. The probability of finding a collision for a hash function depends on the domain of the function. Uh, Option C is we can construct a hash function with a zero probability of collision, and hash functions can be used in the construction of MACs, that is message authentication codes, as well as to generate PRGs, that is pseudo random generators. So, which of the options are incorrect? Okay, so let's go over all the options one by one. Option A is hash functions can either be used for compression or expansion, but not both. Well, while hash functions are traditionally used for compression, they can also be used for expansion. For example, one thing that you can do is take a message, hash it, then add some padding to that hash it again. Do this repeatedly and concatenate all the results. That would give you a much larger string. So hash functions can be used for compression as well as expansion. So option A is incorrect. Option B is the probability of finding a collision for a hash function depends on the domain of the function. Well, this is true because what we can do is we can trivially go over all pairs of messages from the uh, domain and we would end up finding at least one collision. So the probability of finding a collision for a hash function does depend on the domain of the function. So B is correct. Option C is we can construct a hash function with zero probability of collision. Where this is false because recall that one of the basic properties of any hash function is that it has to be a compressing function. That is, the size of the domain has to be larger than the size of its range. And because of this reason, there is always going to be a collision because when the size of the domain is larger than the size of the range, you cannot have a one-one function. So, no matter how we construct a hash function, there is always going to be a non-zero probability of collision. So option C is also incorrect. And option D is hash functions can be used in the construction of MACs as well as PRGs. Well, this is correct. One way to construct a MAC using a hash function is just to do the following. Suppose your message is M. Your tag T would be the hash of M. And we also saw in week 7 that uh, in the random oracle model, we can use hash functions to generate PRGs. In fact, in the random oracle model, a hash function would be a PRG. Uh, Now, ideally, an ideal hash function is a hash function that would map an input to a random element from the range, and all hash functions that we construct are supposed to sort of emulate this ideal hash function as closely as possible. So yes, we can use hash functions to generate PRGs. Is this fine? Okay. Let's move on to the next problem. The third problem is if H and G are CRHFs, that is collision resistant hash functions, then which of the following is or are also collision resistant hash functions? Option A is f1 of x defined as h of x concatenated with g of x, f2 of x defined as h of x concatenated with 1. Uh, Option C is f3 of x defined as h of x concatenated with, XORed with g of x. And option D is none of the above. So which of these are correct? Which of these are also collision resistant? Okay, so the answers are A and B. So now let's see why these are collision resistant. So suppose there exists a probabilistic polynomial time adversary A which can find x1 not equals to x2 such that f1 of x1 is equal to f1 of x2 with non-negligible probability. Then, so what is f1 of x1? It is just h of x1 concatenated with g of x1 is the same as f of x f1 of x2, and f1 of x2 is h of x2 concatenated with g of x2, which implies h of x1 is equal to h of x2 and g of x1 is equal to g of x2. Contradiction, since h and g are collision resistant hash functions. So there cannot exist such a PPTA, and therefore F1 is also a collision resistant hash function. Now, looking at the proof, try to answer the following question. Suppose H were a collision resistant hash function, but G were not. Would F1 still be a collision resistant hash function? Okay, well, the answer is yes, because uh, F1 of x1 equals to F2 of x2 implies that H of x1 equals to H of x2 and G of x1 equals to G of x2. So even if G were not a collision resistant hash functions, if G were not a collision resistant hash function, then this could happen with non-negligible probability, but this cannot happen with non-negligible probability, right? So even if G were not a collision resistant hash function, uh, F1 would still be a collision resistant hash function. And the same is true if H were not a collision resistant hash function. So the point is, even if even if just one of H and G were a collision resistant hash function, F1 would still have been a collision resistant hash function. Is this fine? So if yes, let's move on to option B. Uh, it's pretty much the same as option A, which can find x1 not equals to x2 such that f2 of x2 is equal to f2 of oh, should be f2 of x1 such that f2 of x1 is equal to f2 of x1. That is, it can find collision for h2 with non-negligible probability. And okay, what is f2 of x1? It is just h of x1 concatenated with 1, and f2 of x2 is just h of x2 concatenated with 1. And this implies that h of x1 is equal to h of x2, a contradiction, because h is a collision resistant hash function. Yeah. So f2 is also a collision resistant hash function because such a PPTA cannot exist. Now, over here, we could have assumed that 1 is also a hash function. That is, uh, we have hx1 concatenated with gx1, sorry, hx concatenated with gx, where g just maps any input to 1. Then 1 is not a collision resistant, then g is not a collision resistant hash function, and yet, uh, like, because of what we saw immediately after we saw this, that f of h1, f1 is a collision resistant hash function. After we saw that, right? If even if G were not a collision resistant hash function, F1 would still be a collision resistant hash function. So we could have used that to argue that F2 is also CRHF by just saying that we will replace 1 with G, where G just maps everything to 1. Is this fine? Okay, so then let's look at option C. And let's show that F3 need not be. So to show that F3 need not be a collision resistant hash function, all we have to do is show that exists H and F G, so that F3 constructed using H and G is not a collision resistant hash function. Okay. So what we are going to do is this, that H and G be the same. Rather, let me write like GBH. Then for any A, so for any X, F3 of X is equal to H of X, X H of X stored with H of X is equal to 0 to the n, assuming H is from 0, comma 1 to the, like, instead of all strings to 0, comma 1 to the n. And now it's very easy to find a collision for H3. sorry, for f3, f3 of x1 is equal to f3 of x2, and so f3 is not uh, collision resistant function. Is this fine?
Yes, sir.
Yeah. So then let's move on to the next problem. So the next problem is, which of the following statements is or are correct? Option A is, information theoretic maps are only secure against computational adversaries. Option B is, perfect unforgeability is not analogous to perfect secrecy. Option C is, one-time information theoretically secure MAC is not analogous to OTP or one-time path. And option D is, in the ideal cipher model, only the adversary does not have access to the working of the SPRP, that is strong pseudo-random permutation, used in the given construction. So which of these are correct? Okay, so let's go over this option by option. The first option is, information theoretic maps are only secure against computational adversaries. Well, this is false because information theoretic maps are by definition secure against any adversary. So A is false. Option B is, perfect unforgeability is not analogous to perfect secrecy. Well, this is true because recall that in perfect secrecy, the message was completely secure. That is, an adversary couldn't find out anything about the message. However, in perfect unforgeability, given a message M, given any message M, the adversary can with always guess a tag for M with negligible probability, but this negligible probability is non-zero. So in perfect secrecy, the message is completely secure. However, in perfect unforgeability, the adversary does have the adversary does have a non-zero probability of success. Sure, the probability is negligible, but it is non-zero. So yes, perfect unforgeability is not analogous to perfect secrecy. Option C is, one-time information theoretic secure MAC is not analogous to OTP. Well, yes, this is also true because of the same reason that option B is true. Because when we use one-time pad, the message is completely secure, and when we use one-time information theoretic secure MAC, the adversary does have a negligible but non-zero probability of guessing the correct tag. So option C is also correct. And option D is, in the ideal cipher model, only the adversary does not have access to the working or code of the SPRP used in the given construction. Well, this is false because recall that in the ideal cipher model, every entity involved in the construction, or every entity involved in any security experiment has only Oracle access to the strongly pseudo-random permutation used in the construction. So option D is incorrect. Okay, so is this fine? So if it's fine, let's move on to the next problem. So the next problem is, let f from 0 comma 1 to the n, cross 0 comma 1 to the n to 0 comma 1 to the n be a keyed function, and let h from 0 comma 1 to the less than equals to l to 0 comma 1 to the n, where l is a polynomial function. So over here by this notation, 0, comma 1 to the n to the less than equal to L to the n, I mean all strings, all 0, 1 strings of length at most ln. So let f and h be like this, and consider the keyed function f prime from 0, comma 1 to the n cross 0, comma 1 to the less than equals to ln to 0, comma 1 to the n, where f prime k of m is equal to f of h of m. Then which of the following options is for R true? Option A, f prime can never be a secure PRF. Option B, if f is a secure PRF, then f prime is also a secure PRF. Option C, if h is a collision resistant hash function, then f prime is a secure PRF. And if f, option D is if f is a secure PRF and h is a collision resistant hash function, then f prime is a secure PRF. So which of these options are correct?
D only.
Uh, can you say that D or B?
D, D.
Okay, yeah. So D is the only correct option. Let's see why. Okay, so what we'll do is we'll show that B and C are not correct, and then we'll show that D is correct. And since D is correct, that would immediately imply that A is incorrect. Okay, so showing that B is incorrect, C is incorrect, and D is correct suffices. So let's show that B is incorrect. So for option B, uh, F is secure. Okay, for option B, consider a case or the case where yes, F is a PRF, secure PRF, but H is not a collision resistant hash function. In that case, here's what we'll do is we'll construct a PPT adversary. Uh, so in this case, we'll construct a PPT adversary for F prime. And here's how we'll do it. Rather, a PPT distinguisher for F prime. I lost network connection. So I'd lost network connection for a while. Am I audible now?
Yes, sir, yes, sir.
Yeah. Okay. So what we'll do is in this case we'll construct a PPT distinguisher for F prime. So we have a verifier, we have a distinguisher, and what the distinguisher D prime would do is, so recall that this is a PRF security experiment. So the distinguisher gets to send a few uh, uh, messages to the verifier. The verifier is supposed to send either the output of a TRF or a PRF for these inputs, and then the distinguisher decides whether it's interacting with a PRF or a TRF. So in this case, what the distinguisher will do is just the following. So it will send x1 and x2. Okay, I lost connection again. Yeah. So the distinguisher will send x1 and x2 such that x1 is not equals to x2 and h of x1 is equal to h of x2. Now, since h is not a collision resistant hash function, a distinguisher can find such x1 and x2 with a non-negligible probability. Okay, so then what does the verifier do? It takes B uniformly at random from 0, comma 1. If P is 0, yi is picked uniformly at random from 0, comma 1 to the n. If P is 1, it picks a key uniformly at random from 0, comma 1 to the n and sets yi to be f prime k of xi and sends y1 and y2 to the distinguisher. Now, what the distinguisher does is the following. It checks y1 equals to y2. If yes, it sets b to 1, sorry, b prime to 1. If no, it sets b prime to 0 and sends b prime to the verifier. Okay, now let's analyze the probability that the adversary succeeds, that the distinguisher succeeds. Okay, so let collision the distinguisher can find x1, x2 such that mm, uh, such that x1 is not equals to x2 and uh, h of x1 is equal to h of x2. Probability of collision is non-negligible because we assume that h is not a collision, it's a hash function. Okay, so now let's look at this problem. So the, uh, when x1 and x2 are so that h of x1 equals to h of x2, what is f prime k of x1 and x2 going to be? Well, f prime k of x1 and x2 is just f prime k of sorry, it's just fk of h of x1 and fk of h of x2. So if h of x1 and h of x2 are same, then uh, f prime k of x1 is going to be the same as f prime k of x2. So in that case, y1 would be equal to y2 and the check would succeed. So this happens with probability 1. And what about this? Okay, so in when b equals to 0, uh, in this experiment, the distinguisher is interacting with a totally random function, and the probability that uh, y1 and y2 are the same when they are picked according to a totally random function is just 1 over 2 to the n. We have seen this multiple times in previous lectures, and the reason is the following. Fix any y1 since y2 is independent of y1 and uniform, it's the uniform at random from 0, 1 to the n. But the probability that y2 is going to be that fixed value of y1 is just 1 over 2 p. So, so conditioned on collision happening, the probability that the distinguisher can succeed in distinguishing between a PRF and a TRF, that is between F prime and A TRF is significant, but excuse me, I'm getting a call. Yeah, sorry about that. Yeah, so as I was saying, uh, condition on collision happening, the probability of the distribution is large. But we want to analyze this in general. So what we want to, so what we are interested in is, what we are interested in is this quantity. Sorry, not collision, but just this. Now this quantity is the same as by using the like law of total probability. We would get this is b prime is equal to 1 given b equals to 1 comma collision times probability of collision plus probability b prime is equal to 1 given b equals to 1 comma collision complement times probability of collision complement minus probability that b prime is equal to 0 given b prime equals to 1 given b equals to 0 collision times b prime equals to 1 given b equals to 0 collision complement. So now what we can do is we can keep these two together and these two together and use the triangle inequality to get that. Okay, wait, we don't want to use the triangle inequality. Okay, yeah. So we can, yeah, so this is, so we can forget about these two and just look at these two and we would get, and okay, so this quantity is, we saw that this is 1 minus 1 over 2 to the n. So this quantity is, yeah, 1 minus 1 over 2 to the n times a non-negligible function because probability that collision occurs is non-negligible. So this is non-negligible. Yeah. So we have constructed a PPT adversary D prime, which can distinguish between F prime and a TRF. with non-negligible probability, and so f prime is not a secure PRF if H is not a collagen resident hash function. So option D is incorrect. Is this fine?
Yes, sir.
Yeah. Now let's look at option C. Okay, so now H is a C collagen resident hash function, but so consider case where H is a collagen resistant hash function, but F is not a secure PRF. That so all we need to do is that show that if F is not a secure PRF, or all we need to do is show that for one particular keyed function F, uh, F prime is not is not a collagen resident hash function. So here's what we can do. Let F be this. Rather, yeah, X for all X and so this is a valid keyed. This is a this F defined like this is a valid keyed function. And in this case, we'll show that F prime cannot be a PRF. Why? Because uh, what happens over here is the following. Let's just create a distinguisher V and T. So here's what the distinguisher is going to do. It's going to send X1. Rather, yeah, it can just send X1, one single message to the verifier. And what the verifier does is the usual thing. Cn. If P is 1, then it sets Y1 according to F prime. And in this case, F prime of X1, in this case, F prime of X1 is just H of X1. Okay. And then it sends Y1 to the distinguisher. Now the distinguisher knows H, so it can compute H of X1 on its own. It checks if yes, the distinguisher sets P prime to 1. No, it sets B prime to 0. Sends B prime to the what's the probability that B prime equals to 1 given B equals to 1? When B equals to 1, we are interacting with F prime. So phi 1 is always going to be H of X1. This is 1. And what is probability B prime is equal to 1 given B equals to 0? In this case, we are interacting with a totally random function. So the probability that phi1 is going to be this fixed value h of x1 is just like in option A, 1 over 2 to the n. So this difference is which is not a non-negligible function. So f prime is again not a secure PRF. So this means that option C is also not correct. Is this fine?
Yes, sir.
Yeah, so then let's look at option D. Yeah, in this case, both are secure. Like F is secure, PRFH is a collision resident hash function. Let me add a page. Oh, I added a page in the wrong place. Okay, yeah, so option D. So in this case, what we'll do is we'll reduce the, uh, so we'll use the reduction. We'll show that if there exists a distinguisher for F prime, then there also exists a distinguisher for F. And here's the reduction. So the D prime, so what happens in the reduction? Well, this is a PRF game. So D prime gets to train itself. It sends X1 to XM for training to D, and D just forwards these. Sorry, D just forwards these to V, where X prime I is defined as H of X. Now, what does V do? The usual thing. If P is 0, Yi is picked uniformly at random from 0, comma 1 to the n, and if B is 1, key. It picks a random key and sets Yi to be Fk of Xi prime. And I recall that Fk of Xi prime is exactly equals to Fk prime of Xi. It sends Y1 to Ym to D, D forwards Y1 to Ym to D prime applies with his guess D prime, and D forwards D prime. So all D does is forward a few things and compute a bunch of hash functions. Sorry, a single hash function and a bunch of values. So as long as D prime is PPT, D is clearly PPT. So D is efficient. Now let's look at the now let's look at what the view of D prime is. Because for this reduction to succeed, we want the view of D prime to be a TRF versus F prime view, right? So when B is 0, it should interact with TRF. When B is 1, it should interact with F prime. Let's see what the view of D prime is. The view of D prime. So when B is equal to 1, its view is F prime J. However, when B is equal to 0, that is, the verifier is using a totally random function, D prime's view need not be a TRF. This is if need not be a TRF. Okay, this happens if and only if there exists I not equal to j both in M such that, okay, so without loss of generality, we can assume that x1 to xm are different because otherwise there is no point in sending a string twice. Let's assume that x1 to xm are different. So I don't need to write x I not equals to xj. We just need to write that. Okay, yeah, let me write it. And h of xi is equal to h of x. In this case, uh, yi equals to yj with probability 1. However, in case of a TRF, yi equals to yj should only happen with probability 1 over 2 to the n. So the view of D prime is not a TRF versus F prime view. Is this problem clear?
Yes, sir.
Yeah. So now let's try to fix this. Again, we'll condition on the event of collision happening. So let collision be the event that there exists I naught equals to j in n such that hxi is equal to hxj. Note that probability of collision is equal to order n square times a negligible function in it. Why? Because there are uh, there are order n square pairs over here, and since by assumption h is a collision resistant hash function, for any fixed pair, the probability of collision is negligible. So by union bound, for all pairs, the probability of collision is order n square times negligible in n. Is this clear? Which is itself negligible. Since P prime is PPT, it can only send at most polynomially many queries, so M is poly in N. And we know that when we multiply a polynomial function with a negligible function, we still get a negligible function. So the property of collision is negligible. Okay, yeah. Now, uh, when, okay, yeah, conditioned on condition on collision, so condition on this event happening, the view of is f prime when b is equal to 1. That is when it's interacting with a PRF, and more importantly, a TRF when p is equal to 0. So is this claim clear? Why is this happening? Because when there is no collision, all these xi primes would be distinct. So when we are interacting with a PRF, everything, yeah, when we are interacting with a TRF, the yi's would be independent and random. And when we are interacting with the PRF, there is no count issue because there was no issue in the previous case either. So condition on collision happening, condition on a collision not happening, the view of D prime is a desired view. F prime versus the TRF view. Okay, is this fine? Okay, so now let's look at the success probability of D. So what's the success probability of D? It's this, or rather its distinguishing ability. Probability that B outputs B prime equals to 1 given B equals to 1 minus probability T outputs B prime equals to 1 given B equals to 0. Now, since B just forwards the B prime it gets from D prime to the verifier, this probability is the same as this probability. Okay, and now what is this probability? Again, as we did in option A, let me write it like this. Uh, so for the sake of brevity, I'll skip D prime. So instead of writing for probability D prime outputs B prime equals to 1 given B equals to 1, I'll just write probability B prime equals to 1 given B equals to 1. This is just to make the notation simple. This whole thing multiplied by probability that collision does not happen plus uh, mess this up. This should be 1 given B. Okay, now the claim is this. This is the same as probable, but this is greater than equals to minus this entire quantity. So what's this quantity? It's okay. What I'll do is I'll just upper bound this quantity by 1 and I'll keep this as it is. So I'll get minus a non-negligible quantity. Sorry, minus a negligible quantity. So is it clear how we go from here to here? Should I explain this again? So what's happening is the following. Here are these two parts, right? Now we can argue how to go from here to here in cases. I'll show you one case, the other case is similar. The first case is when this entire quantity is positive. Okay. So when this quantity is positive, what is the smallest possible value of this quantity? Well, if this is positive, the smallest possible value happens when this is as small as possible, right? Now, what's the smallest possible value of this? The, the smallest possible value of this. So, okay, so we know that this is negligible. So the smallest possible value of this entire quantity is just when this quantity becomes the smallest possible, right? And the smallest possible value of this quantity is obtained when this is as small as possible and this is as large as possible. So when this is 0 and this is 1. In that case, this entire thing would be minus 1 and this entire thing would be minus negligible. So we have absolute value of a positive quantity minus negligible, which is just this quantity. So is it clear how we can go from here to here? Yeah.
Yes, sir.
Yeah. So now, okay, there is one more case when this quantity is negative, but the argument, almost the same argument works. Yeah, so try to do that on your own. It shouldn't be too difficult. Okay, so now, what do we know about this probability? Okay, so yeah, let me just write it like this first. Okay, so yeah, before that, we need to analyze this, right? Let me call this one. Now, what is this probability? Probability b prime equals to 1 given b equals to 1 comma collision is not happening. So in this case, b prime is interacting with f prime. Or rather, yeah, I don't need to do this. Let me directly do this. So in this case, uh, b prime is interacting with f prime, and in this case, it's interacting the TRF. So in this case, its view is that of f prime, and in this case, its view is that of TRF. So by assumption, since d prime is a distinguisher for f prime, we get that this is non-negligible in A. What is the probability of a collision not happening? Yeah. So the probability of collision happening was negligible. So the probability of a collision not happening is 1 minus negligible. So now both of these functions are non-negligible. So the product is going to be non-negligible. And the difference, just difference of a like subtracting a negligible function from a non-negligible function gives us a non-negligible function. A contradiction. Because sorry, F is a secure PRF. Yeah. So is this fine? Observe that over here, not only did we crucially use the fact that F is a secure PRF, uh, over here in arguing that the probability of collision happening is small, we also crucially use the fact that H is collision as hash function. So to prove that F prime is a collision, F prime is a PRF, we needed to use both the facts, and that can be seen bec- because like we already saw that B and C are incorrect. That is when F prime is a secure PRF, but H is not a CRHF. F prime is not a secure PRF, and when F is not a secure PRF, but H is a collision resistant hash function, F prime is still not a secure PRF. So yeah, it's no surprise that we had to use both these properties crucially in this reduction. So we have shown B is not true, C is not true, D is true, and therefore A cannot be true. Is this fine?
Yes, sir.
Yeah. If there are no questions, let's move on to the sixth problem. Okay. So the sixth problem is the following. We say that H is a second pre-image resistant function if for all PPT algorithms A, on when given a random input from 0, 1 to the n, A can only find an x prime in 0, 1 to the n, so that Hx equals to h of x prime with negligible probability. So here I should have told you that this h is, let's say, a function from 0, 1 to the n to, let's say, 0, 1 to the m for some m less than n. Okay, so if h is a collision resistant hash function, is it also second pre-image resistant, and is the converse true? So we have to answer these two questions. But before that, is the question clear? Is the definition of a second pre-image resistant function clear?
No, sir. Second, can you repeat what it mean by second pre-image resistant?
Okay,
It's
so
not clear.
we say that a function is second pre-image resistant if there does not exist any efficient algorithm that can find an x prime so that h of x equals to h of x prime when x is random. So it is very similar to collision resistant. However, in collision resistance, x and x prime are arbitrary, right? Over here, x prime can be arbitrary, but x is random. So is it clear now?
Yes, sir.
Yeah. Okay. So uh, would you like to guess which of these is true?
If second pre-image resistant implies collision resistant.
No, no, no. So the question is,
No, sorry,
does
sorry.
collision resistant imply second pre-image resistant? That's this part of the question. And this part of the question asks if what you said, if second pre-image resistance implies collision resistance.
Uh, कन्वर्स ट्रू लग रहा है बट वो
Okay.
वाला ट्रू नहीं लग रहा.
Okay. So yeah, actually, it's the other way around. This is true. The converse need not be true. Let's see why. So
सर कॉलिजन रेजिस्टेंस वाले में दोनों ही रैंडम है, मतलब दोनों ही आर्बिट्री है. रैंडम
right.
और आर्बिट्री में क्या?
Okay. Arbitrary, but they can be anything. Okay. So okay,
हाँ
what
हाँ.
happens in collision resistant? The adversary picks x and x prime, right? And they can be anything the adversary wants, right?
यस यस.
Over here, x is random. And the difference between arbitrary and random is the following. When we say that something is arbitrary, it can be anything. But when we say that something is random, it can't be anything.
इसे
It has to come
अच्छा
from a
फिक्स करना
distribution,
पड़ेगा.
right?
हाँ मतलब कुछ फिक्स करना पड़ेगा एकदम, है ना, मतलब ऐसा कुछ.
Okay, exactly fix नहीं करना पड़ेगा, but it will be random, right? So there is some distribution. For example, when I pick a random x, it can be anything, right? But when I pick okay, let's say I have 0 and 1. When I pick a random number from 0 and 1, sorry, when I pick an arbitrary number from 0 and 1, it can be anything, right? But when I pick a random number from 0 and 1, it's 0 with probability half and 1 with probability half, right? So random has more information than arbitrary. Because arbitrary is anything. Yeah. So second pre-image value is XP.
बट प्रोबेबिलिटी तो आर्बिट्री की भी कुछ भी हो सकती है ना, मतलब आर्बिट्री कुछ भी हो सकता है बट वो भी तो रैंडम ही होगा जब फिक्स
No,
वो
no, no, no.
करने के
So
बाद.
when we say something is arbitrary, there is no distribution. So for a probability for something to have a
ओके ओके ओके.
probability, you need a distribution, right? There is no distribution for arbitrary.
ओके
Yeah.
मतलब हमने एक तरीके से हमने सेलेक्ट नहीं किया है ना, मतलब एक आर्बिट्री है, कुछ भी हो सकता है,
Right. It
ऐसा
can be
कुछ है
anything.
ना.
Right. Yeah. So second pre-image resistance RESI. Okay. Yeah, I should have written here the collision resistant hash function implies.
तो आर्बिट्री वाला मोर स्ट्रांग होगा ही मतलब वैसे लग रहा है, देखने से आर्बिट्री वाला मोर स्ट्रांग है, मतलब कॉलिजन
Okay, right.
रेजिस्टेंस इज मोर स्ट्रांग. या
Right. So that would mean that CRHF implies second pre-image resistance, right? Because this is stronger, this is weaker.
यस सर.
Yeah. So let's show this with like so what we'll basically do is we'll do a reduction. So we have a verifier, an adversary for H. Let me write an adversary for H. Okay, yeah. So this is a so this is an adversary for collision resistant hash function, and we have another adversary for second pre-image resistance. So what this adversary will do is it will pick a random X, send it to a this adversary. This adversary is going to pick an X and this is just going to send xx prime to the verifier, right? Now, okay, x prime not equals to x. So probability that h of x is equal to h of x prime is non-negligible, right? Why? Because ASPIR is an adversary for second preimage resistance, right? So given a random x, it is able to find an x prime so that h of x equals to h of x prime. Okay. So I should mention over here x prime in the question. I should have mentioned it's x prime not equals to x. Yeah. So using an adversary for second preimage resistance, we can construct an adversary for collision resistance. So collision. So this is a contradiction. Because by assumption, since H is CRHF, there cannot exist an efficient adversary, right? Is this fine?
यस सर।
Yeah.
बट इसमें हमने क्या माना है कि एडवर्सरी मतलब ये एसपीआईआर सिक्योर मतलब
Okay. So
सिक्योर
we
नहीं है।
assumed that there is a function H, which is CRHF, but not second preimage resistance, right? So if it is not a if it's not second preimage resistance, there must exist an adversary which can do this, right?
यस यस ओके सर।
Right. So now let's look at the convergence, show why that's not true. So this does not imply. Okay, so consider this function. For some m less than n, uh, defined as follows. Picked uniformly at random from 0, 1 to the n, otherwise. Okay, so hx is almost an ideal hash function, except that for these two strings, for 0 to the n and 1 to the n, it's 0 to the n. So now h is clearly not CRHF, right? 0 to the n is not equals to 1 to the n, but h of 0 to the n equals to h of 1 to the n, right? So h is clearly not a Cauchy resident hash function. However, whenever x is not in 0 to the n, comma 1 to the n. Uh, so when x is not in 0 to the n, comma 1 to the n, in that case, h is a totally random function, right? So we can only find, or rather, any PPT adversary can only find uh, x prime not equals to x, such that uh, h of x prime is equal to h of x with probability 1 over 2 to the n which is negligible in n as long as n is polynomial, right? So whenever x is not either of these two, then the chances of a second pre-match resistant adversary succeeding is negligible. And furthermore, the probability that x is in, this is just 2 or 2 to the n, right? So any PPT adversary second pre-image resistance only succeed.
सर ये भी तो नेग्लिजिबल ही है ना, प्रोबेबिलिटी ऑफ x बिलोंग्स टू 0 n, 1 n
Right,
इक्वल टू
yeah,
2 बाय 2.
okay, with, uh, that's what I'm writing, right? Right, so this is, where is it? Yeah,
तो
this is
इसको हम
negligible
ऐसे नहीं बोल सकते
and this is negligible.
ये भी कॉलिजन रेजिस्टेंस हैज फंक्शन ही हो गया, क्योंकि इसमें तो प्रोबेबिलिटी नेग्लिजिबल ही है अगर आ भी रही है तो.
Right, okay, but okay, what can a collision resistant hash function's adversary do, right? That adversary can pick any two x and x prime, right?
प्रोबेबिलिटी तो नेग्लिजिबल है ना
Right.
अगर.
Okay, so that adversary can pick any two x and x prime such that this happens, right? It is not necessary that one of the x and x prime is random, right? So that adversary knows what h looks like, right? And it can pick
उसकी
any x,
प्रोबेबिलिटी तो
any
वन
y.
होगी, उसकी
What?
प्रोबेबिलिटी वन होगी ना.
Right. उसकी probability 1 होगी. So the probability of a collision resistant hash function adversary would be 1 because of this. And what we showed over here was that the probability of a second pre-match resistance adversary would be negligible. So this function is second pre-match resistance, but not collision resistant. So the implication is not, the reverse selection is not true, right? Is this fine?
ओके सर.
Yeah. Okay, so let's look at the next one now. Which of the following is an assumption in the ideal cipher model? The PRP, or I should write SPRP. F is a collection of totally random permutations. F prime K, where K is can be anything from the key space. The adversary only has oracle access to F and F inverse. Yes, so let me just write SPRP over here. Yeah. For two keys K1 not equals to K2, FK1 and FK2 are random and independent, and all of the above. So which of these are assumptions of the ideal cipher model? Okay, yeah, so let's go over these option by option.
व्हाट इज एसपीआरपी.
Strongly pseudo-random permutation.
ओके.
Yeah. So the first option is the SPRP of the SPRPF is a collection of TRP, totally random permutations. Well, this is true. This is one of the assumptions of the ideal cipher model. The adversary only has oracle access to F and F inverse. This is true. Moreover, in the ideal cipher model, any entity involved in the construction also only has oracle access to F and F inverse. So B is also true. Option C is for two keys K1 not equals to K2. FK1 and FK2 are random and independent. This is also true because like they are totally random permutations which are independent of each other. So all of these are assumptions of the ideal cipher model. Yeah, this was just a recall, right?
एनी
Yeah.
अदर वो assumptions for ideal cipher model
Yeah.
other
Okay.
than
So
these.
yeah. So there is one more assumption. It's just a stronger version of B. So the B says the adversary only has Oracle access to F and F inverse. In fact, anything involved in the construction has only has Oracle access to F and F inverse. Yeah.
Okay, sir.
So now, okay, what's the time? Okay, yeah. So we only have like something like 40 minutes. So let's first look at questions from week 7, and then if we have time, we'll come back to questions 8 and 9. Okay. Yeah. So let's move on to questions from week 7. So
Sir,
the
I have a
first,
question. What
yeah.
what do you mean by random oracle model? मतलब वो डिफरेंस क्या होता है रैंडम oracle और उसमें?
Oh, so we saw a random
सिंपल.
oracle model in class, right? Okay. So in the random oracle model, what do you have? You have an oracle which which implements a random function. Okay. So you have an oracle which implements a totally random function, and whenever you want, let's say the totally random function is f. Okay. Whenever you want to compute the value of any function at, sorry, any whenever you want to compute the value of f at any input x, you have to ask that oracle to give you that value. Okay. So basically, you have Oracle access to a totally random function, and that's it. You don't have access to its code. So this is the random Oracle model.
Okay.
Yeah.
But if you have a given hash function,
Hmm.
then what it means by random oracle? मतलब hash function है फिर random oracle का क्या मतलब है? मतलब कुछ मतलब नहीं है ना?
Okay,
मतलब
so the random Oracle model is an idealized version of a hash function. So ideally, okay, an ideal hash function would have the following property. Given an input x, let's say its domain is codomain is D. Okay. Given an input x, it's going to map x to a random value in D. Okay. This is what an ideal hash function would do. And this is exactly what we do, what we can achieve in the random oracle model, right? However, whenever we have a real, like a real world hash function or any construction of a hash function, it does not have this property that its output is always going to be random. Okay. So a hash function is, so, okay, let me put it like this. Random oracle model is an idealized version of a hash function, and hash function is a real world instantiation, or is, or we hope that a hash function is a real world instantiation of the random oracle model. Okay. So the random oracle model does not exist in the real world. It exists in an ideal world. And the closest we can get to a random oracle model in a real world is a hash function. Okay. Is this fine?
yes sir.
Yeah.
Mm. तो mm, तो अ, तो सर मतलब जो हम बोलते हैं रैंडम ओरेकल तो रैंडम ओरेकल मतलब उसमें हैश फंक्शन का कोई काम नहीं है ना मतलब वो तो अलग से ये कुछ ओरेकल है मतलब
Right.
उसमें हैश
Okay.
फंक्शन.
Right. You are right. So उसमें hash function का कोई काम नहीं है. But when you, but it is an ideal hash function. Okay. When you want to implement that random oracle, that's when you would use a hash function. Okay. So basically, okay, you can have any model you want in theory, right? But ultimately, you have to implement it in practice, right? So how do you implement random oracle model? Using hash functions. So that's the role of hash function in all of this.
हाँ बट वो हैश फंक्शन फिर भी नोन नहीं होगा ना उसका क्या है वो ऐसा
Okay, no, no.
क्योंकि
That hash function would be known. So it's our task. Let's say you have a scheme which uses the random oracle
रैंडम
model.
कैसे होगा
Okay.
वो रैंडम
No,
ओरेकल कैसे होगा मतलब अगर
it's
हम
not a
उससे.
random oracle. So any real world hash function is not a random oracle. So as I said
ओके
before,
ओके.
like you have two worlds, the ideal world and the real world. Okay. In the ideal world, you have a random oracle model. You have a random oracle. Okay. Whenever you want to implement that ideal world, or so you in the ideal world you have a random oracle, and using that you would have some construction. Okay. Let's say of a commitment scheme. Now, when you want to implement that commitment scheme in the real world, you don't have a random oracle in the real world. So you would implement that random oracle. So implement that random oracle using a hash function. But the problem is it, as you said, it's no longer random. So a hash function isn't. So we hope that a hash function would be an approximation of the random oracle. And in fact, that is one of, we saw in class that this thing, that a hash function is merely an approximation of the random oracle, and hash function is not completely random, is one of the disadvantages of this model, right?
Yes, sir. Yes, sir.
Yeah. So yeah, random oracles don't exist in practice. Yeah, that's the biggest problem. So
तो
yeah,
हैश फंक्शन भी तो वैसे प्रैक्टिस में नहीं है, बट प्रैक्टिकल कुछ कुछ है।
right,
बट प्रैक्टिकल जो आप बोल रहे हो कि हाँ, वो भी हमने देखे
right,
ही है, मैंने मतलब अभी तक तो हैश
right.
फंक्शन।
Yeah. So but the hope is, uh, if we can solve some big open problems in theoretical computer science, we should be able to construct hash functions. That's the hope. Yeah, but
ओके
these problems have been open for a very long time.
ओके ओके।
Yeah, but we have practical construction, so it's not that bad. Yeah. So the question is, which of the following is or are true for hash function based commitment schemes? So we saw these commitment schemes in the class. The option A is the collision resistance of the underlying hash function is not necessary for the binding property of the commitment scheme. So over here by the underlying hash function, I mean, yeah, your random oracle or something like that. So yeah, so the option A is the collision resistance of the underlying hash function is not necessary for the binding property of the commitment scheme. Option B is the collision resistance of the underlying hash function is necessary for the binding property of the commitment scheme. Option C is the binding property can only be proved in the random oracle model or ROM. And option D is the hiding property can only be proved in the random oracle model or ROM. So which of these are correct?
CND
C and D. Like, can you repeat that? I didn't hear you properly.
CND
Can you write it in the chat? Your voice is breaking.
C and D options are
Okay, C and
C
D.
and D.
Okay. Okay, D is correct. C is not correct. Yeah. In fact, option B is correct. Okay, so if option B is correct, option A cannot be correct. The negations of each other. So option B is correct and option D is correct. And here's the reason why. So if you recall, what did that commitment scheme do? So to it did the following, right? To commit to M, we computed Y. I think let me call it C. Here H is the hash, the underlying hash function. Okay, so to commit to M, we computed this commitment H of M concatenated with S. Here S is a random string of appropriate length. So let's say the domain of H is of length n and M is of length n over 2, then S would be of length n over 2. I'm not writing those details in here. So uh, suppose we can break binding, and breaking binding would involve would mean finding M prime S prime such that yeah, so that would imply that we have to find M prime S prime such that this out of space. I lost connection again. Yeah, so I lost connection again. Can you hear me now?
Yes, sir.
Yeah. Okay, that was it. Yeah. So breaking binding would mean finding, okay, in fact, it would mean this finding m prime s prime such that m prime is not equal to m, but h of ms equals to h of m prime s prime, right? But this would violate the collision resistance property of the hash function. So to prove binding, we don't need to go to the random oracle model. We can just use the collision resistance property of the hash function in the real world. Is this fine?
Yes, sir. Yes, sir.
Yeah. So, however, to prove hiding, we saw in class we had to go to the random oracle model. Yeah. So if this is fine, let's move on to the next problem. The next problem is choose the correct options from the following. If it should be N, not R. If N encryption scheme is CCA secure, then it is also an authenticated encryption scheme. If an encryption scheme is authenticated encryption scheme, then it is also CCA secure. If an encryption scheme is an authenticated encryption scheme, then it is also CPA secure. And option D is if an encryption scheme is CPA secure, okay, it should be N. If an encryption scheme is CPA secure, then it is also an authenticated encryption scheme. So which of these are correct?
A is correct.
Okay, then okay, okay. So let me tell you the answer. So it's correct answers are B
C. C.
and C. So A is not correct because in fact we saw in class that there exists a CCA secure scheme which is not authenticated encryption scheme, right? I think the scheme was this to yeah the scheme was this to encrypt M. Let's say you have a pseudo random function or sorry a pseudo random permutation from 0 comma 1 to the n to 0 comma 1 to the m. Let me call this fk to compute to encrypt m which is of length n over 2. I would just pick a random string r of length n over 2 and compute fk of m concatenated with r. So we saw in class that this is CCA secure but not an authenticated encryption scheme. So A is not correct. What about B? An encryption scheme which is authenticated encryption scheme is also CCA secure. Well, this is true because a scheme is authenticated encryption scheme if and only if it's CCA secure and has ciphertext enforceability, right? So yeah, so authenticated encryption scheme implies that it's also CCA secure. So B is correct. Now we already know that if a scheme is CCA secure, it's also CPA secure. This we saw a long while back. So if a scheme is authenticated encryption scheme, it is CCA secure. And since it's CCA secure, it's also CPA secure. So C is also correct. Again, option D is incorrect because we in fact know something stronger, right? If something is not CCA secure, if there exists a scheme which is CPA secure, but not an authenticated encryption scheme. Now, since it's CCA secure, it's also going to be CPA secure. So we know of a scheme which is CPA secure, but it is not an authenticated encryption scheme. So A and D are incorrect, and only B and C are correct. Is this fine?
Yes, sir.
Yeah. Okay. So let's look at the next question. So the next question is, there is a server A that wants to broadcast messages to N clients, B1 to Bn, in an authenticated manner. We are not interested in the privacy of the message, just in the integrity and the authenticity of the message. Oh, sorry, each client, not server, each client. So each client, that is B1 to Bn, must be able to verify if the message was sent by A and nobody else. For this, A uses a MAC or message authentication code. What it does is the following. It picks a secret key K and shares this key with all the clients. And then with every message, it appends a tag computed using K. So is the construction clear?
Yes, sir.
Yeah. So the question is which of these options are correct? So A uses a MAC over here. Using a CMA secure MAC solves the problem. Using an SCMA secure MAC solves the problem. Option C is using an information theoretic MAC solves the problem. And option D is none of the above. So would you like to guess which of these is the correct answer?
C, A.
Okay. In fact, yeah, the answer is D, none of the above. And here's the reason. So what is A doing over here? A is picking a key K, and sending it to all of B1 to Bn. Okay. So now B1 has the key, B2 has the key, all the way up to Bn has the key, right? Now here's how B1 can send a message pretending to be A. Let's say it wants to send message M. Okay. Because it has the key, it can compute a tag for the message M using the MAC, right? Let's say the tag is T. Now we can send this message M, comma T to every other client. And what would a client do? It would check if the tag T is a valid tag for message M. But since B1 had the key, it could compute T, right? The correct tag. So in this case, B1 can send a message and a tag to all the other clients pretending to be A. But we wanted that whenever a client gets a message from A, it should be able to verify that it only comes from A, right? So authentication does not work in this setting. Uh,
Yes, sir.
yeah. So the next problem is related to this problem. How can we fix the proposed solution to the previous problem? Like, do you have any ideas? How would you like fix that solution?
डिस्टिंग की ले
Exactly.
सकते हैं ना? हाँ.
Right. Yeah. And that and there are some other technicalities, right? So A picks N keys K1. Sorry, N keys K1 to Kn at okay no, N distinct keys K1 to Kn and shares Ki only with uh, Pi. Okay. Now the problem is A cannot. Now what would we ideally want to do? Suppose A wants to send. So rather, suppose A wants to broadcast. Now, ideally, what we want to do is we want to. Okay, let me first. Yeah, it computes Ti using the key Ki. Rather, let me say it computes the tag Ki. Okay, now Ideally, what we would do is we would send M comma Ti to Bi, right? But over here, A wants to broadcast a message. So how would you fix that? Okay, so here's the message A can broadcast. Wait, how many? There are N, right? For M with respect to key Ki. So is this fine? It wanted to broadcast a message, so it just computes all the tags, appends all the tags, and BI ignores all the tags other than the IF tag. And now, like B1 cannot impersonate A because sure it can compute T1, but it cannot compute T2 to Tn, right? Is this fine?
Yes, sir.
Yeah. There is one more issue. We need to say what MAC, like what security should the MAC have, right? So like that is the security of the MAC, or rather the desired security of the MAC. Well, that depends on the cases. For example,
अ, सर
yeah.
इसमें ये टैग देने जरूरी है क्या एम के साथ ये बाकी सारे T1 T2?
Okay, over here in the question, the like communication model was A broadcasts something to all the clients, right? So it just sends one message to all the clients. So अगर इतने like if we didn't give all of these tags, then what A would have to do is like compute M comma T1, send it to B1, another message M comma T2 to B2, and so on, right? So we are doing this because it wants to send just one big message to everyone, one six common message to everyone.
ओके ओके हाँ
Yeah. So the okay, so now okay, fine. We send this message to everyone, but we also need some security property from MAC, right? For example, over here we have three options: CMA, SCMA, information theoretic, right? So the first option is MAC is random. Sorry, MAC is deterministic. So MAC is deterministic, and B1 to Bn are PPT adversaries. In this case, like would CMA work, would SCMA work, or would we need information theoretic security? Just let me, you can think about this while I write the other cases down. And the third case is B1 to Bn are computationally unbounded. Okay, so in the first case, what should we use? A CMA MAC, an SCMA secure MAC, or an information theoretic secure MAC? Well, since the adversaries are PPT and MAC is deterministic, a CMA secure MAC would suffice. In the second case, since the MAC is random, we need SCMA security. In the third case, since the adversaries are computationally unbounded, we need information theoretic security. rather like information theoretic. So is this fine?
Yes, sir.
Yeah. So let's move on to the next problem. Okay, this problem. Okay, this problem is long. We might not have time. Okay, but let's try it anyways. Okay, so let pi, gen, comma, n, comma, dec be an encryption scheme with message space and ciphertext space both being 0, comma 1 to the n. Now consider the encryption scheme pi prime is equal to gen prime n prime dec prime, where the ciphertext space is now 0, comma 1 to the l plus 1. And the encryption algorithm is as follows. To encrypt m using key k, we encrypt m using key k, but using this encryption algorithm that is of the scheme pi, and then append a 0 to it. Okay. And the decryption algorithm uses the old decryption algorithm, but with ciphertext C1 to L. So C is the ciphertext, and by this notation C1 to L, I just mean the first L bits of C. Then select the correct options. So is the question clear? Or are these two clear?
Yes, sir.
Yeah. So the options are, if the scheme pi is multi-message COA secure, then pi prime is also multi-message COA secure. Option B is, if pi is CPA secure, then pi prime is also CPA secure. Option C is, if pi is CCA secure, then pi prime is also CCA secure. And option D is, if pi is an authenticated encryption scheme, then pi prime is also an authenticated encryption scheme. So would you like to guess which of these are correct? Okay, yeah. So the correct options are A and B. And okay, let's see why. So what I'll do is the following. I'll just show you, since we are short of time, I'll just show you why B is correct. Uh, the proof for why A is correct is similar. Yeah. Let's look at the proof for B. Yeah. So what we'll do is we'll just use reduction. We'll show it that if there exists an adversary for pi prime, we can use it to construct an adversary for pi. So since this is CPA security, there is this pre-challenge training phase. Wait, L over here is the length. That K is the key. Let me say S. A just forwards these to the verifier. The verifier picks the key uniformly at random. Parallel. It picks the key and then it sends C1 to CS, where CI is defined as, okay, then A prime sends, sorry, A sends C1 concatenated with 0 to A prime. So notice that A prime is still getting I prime. Okay. Now this was a check. Now there is a challenge phase. It sends uh, M S plus 1. Yeah, let me just call this M star 1, M star 2, such that M star 1 is not equals to M star. Yeah, I mean, it is. Yeah, let me get rid of this. So in the challenge phase, it sends two messages to the I lost connection. Yeah, so I lost connection for a while. Can you hear me now?
Yes, sir.
Yeah, I keep on losing connection. It would send A prime would send M1 star and 2 star to A, it would just forward these to B, and V is going to encrypt a random over here. So it's going to send this to A. A is just going to send C prime B defined as CB with 0 to A prime, right? Yeah. So now clearly A is, if A prime is PPT, then A is also PPT. So now we are interested in this probability, this difference. Sorry, A outputs A prime equals to 1. Probability A outputs B prime equals to 1 given B equals to 0. Now since A just forwards the B prime it gets from A prime, this is the same as, yeah, let me just copy paste it, it will be fast. Okay, so these two quantities are the same, and because we assume that pi prime is not a CPA secure, A prime is an adversary for pi prime, so this is non-negligible. A contradiction as pi is CPA secure. Okay, yeah, so there is this post-challenge training phase over here. Yeah, let me write it over here. So I didn't draw it, but it's the same as pre-challenge training phase. Yeah, so it's implemented in a similar way. So I didn't draw it. So is this fine? That if pi prime is pi CPA secure, then pi prime also has to be CPA secure. Even if pi is CPA secure, CCA secure, pi prime need not be CCA secure. And what we'll do is we'll just construct an efficient adversary for pi prime. So it doesn't even utilize the pre-challenge training phase. It just sends two messages to the verifier. Yeah, let me copy paste a lot of this from here.
सर ये जो आपने बिट लिखी है कि जितनी बिट
Right,
उसकी दिखी मतलब डिक्रिप्ट होंगी,
right.
तो उस जितनी हमें शो होंगी ना डिक्रिप्ट करके उसमें डिपेंड करेगा ना मतलब जितनी मतलब अगर वो पॉलिनॉमियल टाइम है तो आई थिंक ऐसा कुछ
Yeah.
है क्या इसमें?
Anyway, it's not polynomial type. Yeah, so you are somewhat close, but it's not exactly that. So let me just quickly write the reverse link. Okay, now what A will do is the following. Let's say C is equal to C prime 0. So this is what n would do, right? It would use uh, this is what n prime would do. It would use n to encrypt f and then append C. Now what A would do is the following. A prime would do is the following. It would send C double prime is equal to, rather let me call this C star. So it would send C prime with 1. This would send uh, the verifier would send M, which is and M1. In this case, B is equal to 1. Otherwise, B equals to 2. Or, yeah, or rather, yeah, I should call B is equal to 0, B is equal to 1. Or yeah, P prime equals 1, P prime equals 2. Like generally we use 0, 1. Here I'm using 1, 2 for some reason. Yeah. Okay, so now claim is my claim is that this probability is 1. And this is because of the following reason. Look at what the decryption scheme is doing. It's completely ignoring the L plus 1th bit, right? So even if I, even if C prime concatenated with 1, over here it would completely ignore this and just decrypt C prime. The decryption of C prime would exactly be MB. Now notice over here that this is not a valid ciphertext. However, it's not, the decryption algorithm is not performing a check about whether this is, for that reason we are succeeding. So this proves that pi prime need not be CCS secure. And in the reduction, we never use the property that pi prime. So, okay, so C is not correct, and therefore D is also not correct, because the exact same argument would also work in the case of D, because when is some scheme authenticated encryption scheme, right? That's to be CCS secure and ciphertext unforgeability. But we saw that pi prime is not CCS secure, so yeah, it would also not be authenticated encryption scheme. So is this fine?
Yes, sir.
Yeah. So we are out of time. So if there are no other no questions, we can end the session today and meet next Saturday. Sajay,
यस
first
सर।
become, yeah,
सर आपसे एक चीज पूछनी थी कि आप पीएचडी कर रहे हैं क्रिप्टोग्राफी में?
PhD but not in cryptography.
सर आप ऑडिबल नहीं थे, एक बारी और बोल देंगे आप
Oh,
क्या?
okay. I am doing a PhD but not in cryptography.
इन विच एरिया?
Complexity theory.
ओके ओके, कॉम्प्लेक्स।
Yeah.
ओके सर।
Yes, if there are no other
सर
questions, then yeah.
कैन यू प्लीज टेल मतलब अगर कॉम्प्लेक्सिटी थ्योरी कहीं से पढ़नी है बेसिक, वो कहाँ से पढ़ सकता है?
कोई
Okay, there is this book. Okay, let me write it in the chat.
yes.
Oh yeah, this one. Computational complexity, a modern approach. Arora and Barak. Like, okay, but from like some chapters of this book are like, yeah, some chapters of this book are difficult. But I think for basic complexity, you can just read chapters 1, 2, 4. Yeah, 1, 2, and 4 should suffice.
सर ये कॉम्प्लेक्सिटी थ्योरी में ही आता है जैसे एवरेज केस कॉम्प्लेक्सिटी वर्स्ट केस कॉम्प्लेक्सिटी ये
Right, yeah. But in complexity theory, you mostly study worst case complexity. There is a sub area which also studies average case complexity. In most cases, you study worst case complexity.
कैन यू डिस्टिंग्विश बिटवीन बोथ मतलब
Okay,
एवरेज
so
एवरेज में ये होता है क्या कि हर इंस्टेंस हार्ड होता है उसका ऐसे कि every instance of the problem is hard.
no, no, so in worst case complexity, so given a problem P, the worst case complexity of P is the complexity of solving the most difficult instance, right? So like look at all the instances of P, which one takes most time? That determines its worst case complexity. Okay. In average case complexity, what you do at a very high level is the following. You pick a random instance of P and look at its complexity.
Okay, okay, yes.
Yeah. So if there are no other questions, we can meet next Saturday. Bye. Thank you.